Okay, I'd like to welcome you all to this webinar sponsored by the Chicago DOE Alliance Center here at the University of Illinois at Chicago. This week, we're pleased that James Walsh from the University of Massachusetts Amherst has graciously agreed to give us a talk. James is an assistant professor in the chemistry department at UMass, where he has launched a research program focusing on high pressure techniques, solid state synthesis, and X-ray crystallography. James is from Manchester, England, and received his master's and PhD in chemistry from the University of Manchester. And after a postdoc in Denmark, he moved to Northwestern in 2015, where he was a postdoc with Dana Friedman, but also began working with Steve Jacobson, a CDAC partner, and became very active in CDAC and became an active user of the APS, HPCAD, and other sectors, exploring new materials such as intermetallics and new magnetic materials, electronic materials synthesized and characterized under pressure. And in 2019, James was appointed assistant professor at UMass, and today he'll tell us more about his recent work. So over to you, James.
Thank you, Russ. Thank you for that introduction. I'm excited to give the talk today. The CDAC seminar, I've been watching them. They've been a great series, some excellent speakers, and I hope that I can live up to that standard set by those great speakers. And in particular, as you mentioned, I think CDAC is a great venue for presenting this work because it was in large part supported by CDAC through Steve Jacobson's partnership. So even though I'm showing sunny Amherst in this photograph, a lot of this work was carried out in the Chicagoland area. And so that's what we'll be talking about today. Okay, so my research interest, as Russ mentioned, is solid state materials chemistry. And the reason I find this field particularly exciting is that materials really underpin technology. That is to say that a lot of technologies that we have rely on materials properties. And without those, we wouldn't have those technologies. So for example, we have renewable energy technology. So, wind turbines that can convert wind energy into electrical energy rely on having permanent magnet materials. And in particular, we use neodymium iron boride more than any other magnet for this purpose because it is so efficient at converting energy, the wind energy into electrical energy. It's a good permanent magnet. If we had different permanent magnets, that efficiency wouldn't be as high. And so in that sense, the efficiency of renewable energies really relies on materials properties. Another example would be deep earth drilling, or really any machining properties, which rely on having super hard materials. Compounds that have extremely strong bonds, like diamond, or in this case, I'm showing a couple of other widely used compounds, really strong bonding that allows them to resist fracture and wear, and allows us to use them for machining applications. So again, this is a chemical property, arises from chemical bond strength, but it allows us to do things in the real world. It allows us to use technologies that we otherwise wouldn't. A more niche example, nuclear fusion, which relies on superconductors. Another example would be MRI instruments, which also rely on superconductors, and that's because they generate these very high, stable magnetic fields, and that really you can't pull off with normal conductors. So superconductors are required, and I'm showing a couple of examples here of the most widely used superconducting materials right now: the niobium titanium alloys and the niobium tin intermetallics. Another example, a bit more far out, would be space exploration, which relies on thermoelectrics. So when you send a spacecraft far away from the sun, you can't really rely on solar energy anymore. And so you need some other way to generate electricity in the spacecraft. And so they use thermoelectric materials, which are able to convert heat into electricity. And so the heat is some radioisotope thermal generator. So some material that's radioactive that is constantly, over many years, generating heat. And with materials like bismuth telluride, we can convert that heat energy into electricity. So it's a material that is allowing us to have a technology to do something, but it relies really on the material's properties. And it's fair to say that without these materials, these technologies that I've listed would not be as efficient and perhaps wouldn't be used. And you can apply that same logic to materials of the future. And so they will also rely on certain properties, and it might be that those properties we don't have yet. We may not have the materials required to perform that particular technology. So an example, asteroid mining. This is something you read about in New Scientist sometimes, in popular magazines. We don't do this right now, but people are thinking about it. To be able to do this, you would want to have, again, super hard materials to perform drilling. But in this case, when you're out in space, you can't just replace the drill bit like we do on Earth. And so you would probably want something that lasts longer than the super hard materials that we have right now. But what that looks like, we don't know. We haven't necessarily discovered those materials yet. Another example would be hypersonic flight. So we actually do have the technology already to design aircraft that can travel at hypersonic speeds. What actually limits them being used is that they tend to melt. So the nose cone, when they go to extremely high speeds, the heat at that nose cone is so high that the materials break down, and then you don't have a functioning aircraft. And so what we need for those technologies would be new materials with even higher melting points than what we currently have. And another example, quantum technology. This is a broad area that's of course of interest to many people right now. And this will require materials that we don't have yet that have entangled states or superposition states within that material. And what that looks like, we don't know. We just know it's going to be complicated and quantum. So that's the reason that I'm interested in materials science. So then the question is, how do we find new materials? I've hopefully made the case that we don't have all the materials right now that we'll ever need. So how do we find new ones? And there are a few approaches that we can take. So one, we term exploratory synthesis. So you just take two elements and you try to react them together. You try to do chemistry by heating them, and you see what you end up with, and you see whether that's a new material that's different to what you put in. And of course, this is how we discovered a long time ago now bronze, which is an alloy of copper and tin. So if you mix it in the right proportions, around 90% copper, 10% tin, and you heat it up, and then you cool it back down, and you see what you get, also known as cook and look chemistry. What you find is that the bronze has different properties to either copper or tin. It's more resilient, which means you can fashion new materials that you couldn't from stone. So that's why we had the Bronze Age. So it's of course a simple old example, but it illustrates the idea that sometimes you just do it for the sake of doing it. And I think there's nothing wrong with that. This is exploratory synthesis. You just want to see if anything interesting falls out when you do the chemistry. Another approach you might have is what I would term completionism. So it might be that you have some series of materials that you know have good properties, and when you catalog it, you might see that there are certain analogs within that family that you haven't accessed yet. And so this is an anecdotal story about the niobium tin alloy that I mentioned earlier on in the introduction. The story goes that the reason that they did this reaction looking for the niobium tin was that they'd already explored the other elements, the other alloys, I should say, nearby in the periodic table, and someone noticed that everything that they'd looked at so far almost makes a Union Jack. And so by doing the niobium tin, it would complete the Union Jack. That's not really hypothesis-driven science as we like to aim for, but it's as good a reason as any. And it turns out that yes, the niobium tin now is the most widely used superconductor. So MRI instruments are the market share. Around 80% of superconductors are used in MRI instruments, but also more advanced instruments like particle accelerators and synchrotrons. Okay, and so another approach, which is obviously much more modern, is to use computers. So the idea here is that we have theory that helps us to understand or predict from first principles that if we have this element with this element in this structure, we should be able to calculate with quantum mechanics the properties that we need. Now, we've come a long way in this, and I say we, I'm not a computational chemist, but we're at the stage now where computers can actually do a lot of predictive, very, very powerful predictive calculations without necessarily us having to go into the lab. We can really just have it generate a structure and do the calculations to find those properties. And so this is an example of Tony Stark, also known as Iron Man. This is a scene from Iron Man where he is, you could say, computationally exploring the cerium dysprosium system. I think in this scene, he's actually trying to make a new element. So probably much higher pressures than we would go to. He's trying to do nuclear fusion. But the principle is the same, that he's not having to go into the lab and handle these elements, but he's using knowledge and computation to get to the answer and to predict whether that's a promising avenue. Doesn't actually look like this. We can do this kind of science. It looks more like this photograph. But hey, if you know Unix, then you can usually get started pretty quickly. This is the general approach that a lot of people are using for materials discovery, is that we can calculate enthalpy. And so this is kind of a simplification, but this is something that we can readily calculate. And it turns out this is actually a really powerful metric for stability, to be able to say that a given compound will have a negative formation enthalpy is a really powerful way to predict whether it will be synthesizable. And so we've seen a lot of good talks already throughout the CDAC series working in this type of area, where you do computational prediction within a system, you do crystal structure prediction, and then you follow that up with experiments. And so that really helps to direct materials discovery without having to do all the exploratory synthesis. Okay, so in this talk, I'm going to be focusing really on bismuth. So a lot of these projects involve bismuth compounds, and the reason that we chose this system to look at is that bismuth is an interesting element, even by itself. So not even considering the compounds yet, just by itself, bismuth is interesting. It's the only pure element to exhibit non-conventional superconductivity, which is kind of weird. It's the heaviest non-radioactive element, so you have to go to radioactive elements to have a higher mass. But with bismuth, it's non-radioactive. It's also non-toxic, pretty safe to use. We actually use it in Pepto-Bismol. There are a couple of other weird things about it. It has a lower density in its solid form than its liquid form, which is unique among the elements. And it has, for a metal, a very low electrical and thermal conductivity. And so it's kind of an outlier and a special material. And it's heavily studied by a lot of people because it tends to give interesting compounds. Two that I'll highlight just here are the manganese bismuth intermetallic compound, which is a permanent magnet. Actually, at one point, it was the best permanent magnet we had in the 50s, just before the discovery of the rare earth magnets. Manganese bismuth was heavily researched as a permanent magnet. Another example would be nickel bismuth, which is a superconductor. It has a transition temperature of around 4 Kelvin, so it's not really used industrially, but still it's an interesting, relatively high temperature transition. So there's clearly something special about bismuth, and that's the reason a lot of people are interested in these bismuth containing compounds. Excuse me. Okay, so we've made the case then for why we want to explore bismuth, why we want to look for new bismuth compounds. So how do you do that? Manganese bismuth, nickel bismuth, they already exist. So that means someone's already gone and done the exploratory synthesis approach. They've taken those elements, they've mixed them together, heated them to see what they get. So how do then we find new materials in already explored space? Well, the answer is you expand your phase space. You find some other parameter that you expect should have an effect on synthesizability, and you use that as your synthetic variable. And so that for us, it turns out, is pressure. So I did originally start looking in the iron bismuth system, trying to make new iron bismuth compounds using other techniques that have been shown to be able to access metastable materials like nanoparticle synthesis. Electrodeposition didn't really go anywhere. Pressure turned out to be the key. And so that's really why we now talk about it. And I don't talk about nanoparticle synthesis. So then the question is, how do we access high pressure? So if that's something that we want to explore, how do we actually do that? I think this audience does not really need an introduction to the diamond anvil cell, but one thing I do want to point out is that the ability to do in situ X-ray diffraction in the diamond anvil cell is extraordinarily powerful. And so, especially as a synthetic chemist, this allows us to, with in situ X-ray diffraction, while we're doing the reaction, monitor in real time whether we have a reaction occurring. So usually we use X-ray diffraction in solid state chemistry after we've done the synthesis. So you spend a few days doing the synthesis, and then you take the crystals that hopefully form, and then you do the analysis and you try and figure out what you made. With the diamond anvil cell, we're able to do in situ X-ray diffraction, monitor the reaction in real time. And that's extraordinarily powerful. And so the diffraction that we're able to access is because of this conical aperture in the diamond anvil cell. And so we're at the stage where we have this 80-degree conical aperture is more than enough to do what we need to do, especially with the high energy of the synchrotron sources. Okay, so then how do we actually perform the reactions? So we know that to do chemistry, usually you need heat. You need to raise the temperature enough to break bonds, induce diffusion, and give the system the energy it needs to form a new product if it's indeed going to react. And so the way that we do that is using the laser heating table. So this is the laser heating table at HPCAT, sector 16, at the advanced photon source. And so what we're doing is heating the sample from both sides. So these are optical mirrors that are placed in the beam path. So the beam is going through everything. But we can move these mirrors in, and that allows us to direct laser light from both sides, upstream and downstream. So heating the sample from both sides to extraordinarily high temperatures. So we can actually get to thousands of degrees Kelvin with this approach. I typically don't go that high unless I do something wrong and I'm not paying attention and it couples and runs away. Usually we're around 1,000 to 1,500 Kelvin, but you could go to much, much higher temperatures with the laser heating. And what this allows us to do then is have really, really fast feedback from the reactions as we perform them. We can be collecting diffraction on, we typically use the seconds scale, 5 to 10 seconds. We're collecting a new image and looking at it in real time. And I'll show an example of that. Okay, if we're using laser heating, then we have to do something special with our diamond anvil cell, which is to insulate the sample. And so we do that by using magnesium oxide. So magnesium oxide allows us to basically sandwich our sample between two pieces of magnesium oxide. I'll show on the next slide how we make those. But this is ideal because it serves multiple purposes. So not only is it a thermal insulator, which insulates the sample from the diamonds. If you didn't have that, you'd be just heating the diamonds, and you wouldn't really be able to efficiently heat the sample. But not only is it a thermal insulator, it also serves as the pressure transmitting medium, the pressure calibrant as well. So we know the equation of state of magnesium oxide. So that allows us to look at its lattice parameters to get to the pressure that we're at in situ. And it's also chemically inert, we presume, with a very high melting point, and optically transparent. So really it's perfect all around for this purpose. Here's how we make the MgO. So this is a technique that we learned from the staff at HPCAT, Ross and Yue in particular. I'm showing it here because I think it's something everyone should be aware of. I think a lot of you already do use this, but if not, you should really look into it, because for synthesis, it makes so many things much more straightforward and repeatable. And so what we're doing is we take a single crystal of magnesium oxide. Usually it's pretty thick to start with. We attach it to a glass slide with glue, and then we grind the sample down. We aim usually for our experiments to a final thickness of around 15 microns. And then we use the laser drill at HPCAT. This is the laser drill that Ross Rubiak put together. And so with this, we can machine out, basically by blasting away the MgO with this motorized stage, circles of MgO, discs of MgO that are 15 microns thick with a total diameter of whatever we decide. And so we make that be usually just a little bit less than the gasket sample space. And so then we can take those and we can load our samples in this way. The reason this is especially useful for us, if you're dealing with oxygen sensitive materials, such as finely ground metal powders, which can oxidize, and they more readily oxidize when they're fine powder because the surface area to volume ratio is higher. Then if you have to load in a glove box, being able to use magnesium oxide actually makes things a lot more straightforward. And so we typically will put one piece of the MgO sandwich in the gasket, the other piece on the opposing anvil, and then we close it up in the glove box after having dropped the sample into that space. So this is more technical detail that I would usually give in a chemistry talk. I think it makes more sense in this venue. Please reach out to me if this is something that you want to know more about, because I really do think this is a great technique and it can really be transformative. We tried a few things before figuring this out that did not really work. And you sometimes really have to use a glove box, or else you're just going to get wayward reactions. Okay. So let's take a look at an example reaction then. So there are a few steps. The first one is that you need to find a place to heat with your laser heating spot that has the elements that you're trying to react. And that's not trivial. This is kind of an extreme example, but here we're showing the powder X-ray diffraction between two different sites. So this is just the absorption scan, the transmission scan maybe of the sample space. And what we see is that at this spot, we don't have iron. So these red bars would have peaks. If we had iron present, we don't have that, whereas site B does. And so site B is a place that we should go and do the reaction. As I said, this is kind of an extreme example. You would hope that you don't get regions of, in this case, purely bismuth. We've kind of figured out some of the sample processing since this time, but it illustrates the point that you need to be able to know where you're heating, and that's something that you can do on the beamline quickly. You can very quickly just measure where you want to start your reaction. Then you heat while you're under the pressure that you've tightened the DAC to, and you look for signs of a reaction, which in this case would be the growth of new crystalline peaks. And so that's what we are plotting here. If you look at certain regions, you'll see that there are peaks growing in. These peaks are from a new phase. So we had iron and bismuth and MgO peaks to start with, but over the course of heating to 1400 Kelvin at 32 GPa, over the course of around 10 minutes, we've created new peaks from a new phase. You find a spot that has a good conversion and you index those peaks. And so this is something that's not trivial. To be able to index a phase, you usually need pretty good data. At the synchrotron, you can get that. Because we have relatively wide conical apertures and high energy, we actually get a lot of the reciprocal space measured on our detector, enough peaks to be able to do this kind of analysis. And so what we find in this particular case is that we can index to this tetragonal space group I4.cm. We can index the unit cell parameters. And so then the next step would be to solve the phase. And this could be done in many ways. In this case, we find a match to this unit cell to the structure type. And in fact, there are a couple of other phases that are similar, a transition metal and a main group element, that adopt this structure type under pressure. And so it kind of pointed us towards this being iron bismuth. But you could also, in theory, do Rietveld. I think that's a bit more tricky. I don't think you really would get the quality of data that you need to do a Rietveld solution of a phase, but you can at least do refinement if you can get to the phase another way. As I said, what we do was really using databases to match. We could also use DFT, and I'll come back to this and mention this later on. We could use those crystal prediction approaches to try to get the answer. And so this is what we get. This is the iron bismuth compound. We published this in 2016. What's exciting about this material, and for me personally, it was exciting because I spent a year doing, different kinds of chemistry that went nowhere, was that this is the first iron bismuth bond in the solid state. And so you can see that 30 GPa, this interaction between the iron and bismuth is 2.72, which is within the expected bonding radius for this structure type. And so we've made this intimately bonded compound in a system that, until that point, didn't seem to be reactive. And so that was exciting and made possible by the beamline and support from CDAC. Otherwise, I'd have been trying nanoparticles still probably. Okay, so another system that we investigated was the copper bismuth system. And in this system, we found the first copper bismuth compound, which I'm showing here. And what I hope that you'll see immediately is that this is a pretty complex structure. It's remarkably complex, in fact. You know, sometimes we think that as you go to higher pressure, you get something more simple. So I think was the belief for a long time. We're starting to see more and more examples where that's not the case, that high pressure may not actually just be the closed packed structure types. And so in this case, we see some phases remarkably complex. And inside the phase, if we look, we can see hints of phase separation. So even though we've made this compound, there are still signs that the copper and the bismuth don't really want to be intimately bonded. And we can see that from these copper 5 trigonal prismatic moieties. So the copper is bonding to itself. And then we have these bismuth channels that run along the C-axis, where the bismuth is kind of staying to the other bismuth atoms. And so this is interesting to note that we can get this kind of complexity in a simple binary system. You know, the unit cell is relatively large for this system. So this was at 6 GPa and heating to 800 Kelvin. The nice thing about having a relatively low pressure, so with the iron bismuth, we had to go to 30 GPa. And this copper bismuth, we only needed to go to 6 GPa. And so what that allows us to do is to use large volume press methods. And so in the large volume press, it's larger in scale, so it's not a handheld device anymore. It can take up, you know, half a room. But the benefit is that we can have a much larger amount of sample. So we can get to cubic millimeter scale samples in the large volume press. And so we did this work at sector 13 at GSE CAS, 13 IDD. We were able to scale up the synthesis of copper bismuth. And I'm showing here the schematic. This is where the mixture of copper bismuth would go. You have this thermally insulating surrounding jacket. This is a heater, so we can drive a current through the graphite heater, and at the same time we can monitor with a thermocouple the temperature. So we're still able to do our synthesis. You know, as chemists, we want to control temperature and pressure, and we can do that with this setup. And what's nice is that we create the copper bismuth, and it's quenchable. And so because it can be quenched, in other words, you can remove the pressure and still have that compound. It's not always the case. We usually hope that it is, but sometimes it just isn't. Because you can do that with copper bismuth, it allows us to do other measurements ex situ. So we can now take it away from the high pressure conditions and be able to do analysis that we can't really do in the diamond cell, or at least we couldn't. And so one of those is the measurement of its bulk resistivity. And when we do this, we detect actually that it's a superconductor, relatively low temperature, 1.4 Kelvin. But this is something that we wouldn't have been able to determine otherwise in the cell. Because we can grow single crystals, this is a single crystal recovered from the large volume press reactions, around 10 microns. That's big enough, even with laboratory sources, to be able to do X-ray diffraction. When we do this, we find it's even more complex than we thought. So I said on the previous slide that the copper bismuth system is remarkably complex. It's even more complex than that because it's a modulated supercell. It's a modulated structure. And so what I'm showing here is the modulated supercell. And so that means that we don't have, we have channels of disordered copper 5 moieties, which can coexist in the model with bismuth atoms. And then we have channels of ordered copper 5 moieties and bismuth atoms. And so that's really interesting. So this was work done by Samantha Clark, now at Lawrence Livermore. She's an excellent crystallographer and was able to solve this crystal structure. But again, we would not be able to see this kind of complexity just using the diamond cell data. So another system, nickel bismuth. So we know that nickel bismuth already has compounds under ambient conditions, but is there anything that we can discover in the phase space opened up by pressure? It turns out there is. So this is an interesting example of now taking, rather than a mixture of powders, we're taking a single crystal of an intermetallic, and you can see the hexagonal facets on this. This is a hexagonal system. This is a single crystal, really beautiful, which we then crushed and put into a diamond cell, but it's a pure nickel bismuth. And so what we find is that when we heat above 37 GPa, we see this phase transition. So over the course of 5 minutes, we get this conversion from the original, what we now call alpha nickel bismuth, into a new phase, which we call beta nickel bismuth. And so this is a essentially a buckling of what was this linear chain of nickel atoms. And so what would be really nice is if we could somehow measure the superconductivity of this phase, because these two phases are pretty similar. And so we might be able to learn something from having this now buckled nickel chain and what effect that has on the superconductivity. And so another example from the nickel bismuth system. Now we're taking the other known intermetallic. So again, this is something that we can make under ambient or under normal solid state conditions, nickel bismuth 3. When we heat this under 15 GPa, we get a transformation into this 1 to 2 phase. This is a new solid state phase that was published. What's interesting is that if you actually look and you compare the original nickel bismuth, you see these one-dimensional, pseudo one-dimensional building units. So these, you see the 2 nickel surrounded by these 6 bismuth, kind of, extends into the screen. So it's not quite that simple, but you can see this moiety. What we find is that when we apply pressure, so the higher pressure we go to, we actually increase the dimensionality, we could say. And so we could say that we're controlling the dimensionality with pressure. So these are pseudo one-dimensional. The moieties appear in this higher pressure system as 2-dimensional sheets. And then the same moieties appear in the beta nickel bismuth that I showed in the previous slide as these 3-dimensional connected frameworks, basically. And so that's an interesting observation that, again, Sam published on. So we have manganese bismuth, another system. Again, the 1-to-1 manganese bismuth was already known. This is a permanent magnet material, as I said, that was investigated heavily in the 50s for technical applications, but still now you'll find papers where people go back to this 1-to-1 compound and try to understand where its magnetocrystalline anisotropy comes from. What we were able to do is take that compound, heat it under pressure, and create a new compound, manganese bismuth 2, so the 1-to-2 compound. It's actually analogous to the iron bismuth compound. And what's interesting about this is that we see these remarkable similarities between these two pretty different structures. So in both cases, we have these linear chains of manganese atoms along the C-axis. You can see that here as well. And they both are surrounded by a different number of bismuth atoms. This one's surrounded by 8, nearest neighbor. This one's surrounded by 6. But they all have, they both share this alternating pattern of the top and bottom faces. And so that's kind of an interesting thing to point out. And so it's possible that this is a new permanent magnet material. Unfortunately, it doesn't quench. Just like the iron bismuth, we lose it around 3 GPa. But the nice thing about modern computational chemistry being what it is that we can still investigate this phase. Even though we can't really recover it and do the bulk measurements that I described for copper bismuth, we can still use density functional theory to get an idea of whether it's a permanent magnet. And so in this experiments, these were carried out by our collaborators at Northwestern at the time, the Rondinelli group. It was Danilo who actually did this work. But what we can see is that the ferromagnetic configuration has a lower energy than the rest. So as long as we've tried every possible, in this case, Ising configuration of the spins, we should be able to compare and rank by energy and see which magnetic state is the ground state. And so it indicates that we have a ferromagnetic ground state. So manganese bismuth 2 then presumably is a new ferromagnet and perhaps a permanent magnet. And so this is something that we would like to be able to study further if we could find a way to quench. This is true for many of the materials that don't quench when we remove pressure. We'd like to find a way to be able to do that so that we can study with our traditional bulk techniques. And so the last binary system that I'll talk about, this is recent work. This was actually published this year. So this is Alison Altman at Northwestern. She's a postdoc at Northwestern in the Friedman group. And so she published this really nice paper in JACS about the molybdenum bismuth system. So now we've moved away from the first row of transition metals into the second row of transition metals. And what's nice about this paper is that this is the first time we've actually used these crystal structure prediction methods. Early on, we did collaborate with the Wolverton group at Northwestern. So Max gave a really nice talk last September about his approaches. So this is kind of the same approach. It's not. There are obviously differences in all of the crystal structure prediction packages, but we're ultimately using enthalpy calculated through DFT to predict whether a certain compound will be stable. And so this is something that we were able to do in our group in-house. We had fun learning this program, and I want to give credit to Chris Picard at Cambridge, who wrote the ERS package that we used. And if you want to learn more about this, you should go to this link. It's really something that anybody can get into, I would say, and that's a credit to Chris and other computational scientists who've made this something that's accessible without necessarily having the theoretical background. So it's really exciting that we're actually able to do these calculations to direct the synthesis really for the first time. And so what Alison found when she heated this was that the molybdenum bismuth 2 compound is synthesized. Again, it's an analog to the iron bismuth and the manganese bismuth. And so it seems like this copper aluminium structure type actually seems to be pretty common for transition metal bismuth compounds. Which was also able to see is that you get a lot of low energy or low line structures that are basically BCC derivatives. So these two are probably not real ordered intermetallic structures, but it's showing us that alloys are perhaps stabilized, and we actually do see evidence in the diffraction that alloying seems to be present. Okay, and it's not just binaries, so I don't need to think that all we do is 2 elements with bismuth. We sometimes do 3 elements with bismuth, and so this is an example of the discovery of bismuth vanadium perovskite. So this is something that had been published on in the past in the context of why isn't bismuth vanadate perovskite synthesizable, and it's because you have a redox reaction where the vanadium 3+ is reduced by bismuth. And so, sorry, is oxidized by bismuth. This is avoided at high pressure, and it turns out that you can actually synthesize and recover bismuth vanadium perovskite. And so this is presumably due to changes in things like electronegativity. So Martin Rahm gave an excellent talk in CDAC at the CDAC seminars about this change that pressure induces on these very fundamental chemical concepts. And so things that are assumed impossible turn out to be at high pressure often possible because you've changed these fundamental parameters. Okay, so the last thing I want to mention is that we don't do just synthesis. So another area that we're interested in is quantum materials, and in particular magnetically frustrated systems. So again, another example of a great talk in the CDAC seminar. Daniel Haskell from APS talked about his work in quantum spin liquids. I'm going to be much more brief because I don't know as much, but the concept behind frustrated systems is that you can sometimes have systems where there's an exchange interaction, a magnetic exchange interaction, which just means a preference for having spins aligned in a certain way that cannot be satisfied by the geometry. So an example would be antiferromagnetic exchange in an equilateral triangle. And so that's what we're showing here. There are 8 ways that you can arrange those Ising spins, 8 different configurations. 2 of them are clearly very high energy because these are all ferromagnetic interactions. It's not going to be happy with those, so we color those red. And then there are 6 that are equally not perfect. So in none of these do you have antiferromagnetic interactions between all 3. It's just not possible to arrive at that. But you have this highly degenerate ground state of equivalent energy spins. And so this is something that you can see in when you extend into 3 dimensions or 2 dimensions. You can actually extend this, what we call frustration, into the bulk. And this highly degenerate ground state then becomes even more degenerate, if that can be a thing. You have many more states within that ground state, and that can lead to exotic properties, one of which is quantum spin liquids, as Daniel was presenting on. And so we investigated the potassium ion jarosite mineral compound. So this is a mineral that occurs naturally, but we can synthesize it in the lab. So we can make it so that it's purely potassium, purely iron jarosite. We can grow single crystals. This is a mineral that has spin 5 half ions arranged on what we call a Kagame lattice. So it's called a Kagame lattice because it's a basket weaving technique from Japan that has basically the same, it's the same lattice. But this can be thought of as a 2D lattice built from triangles. So these vertex sharing triangles extend into 2 dimensions in this case, and that frustration is extended. And so you can imagine that in an ideal system, if you had spins that were trying to orient antiferromagnetically, they wouldn't be able to achieve that ground state. So the idea we had, actually the original idea for studying this system, was to try to make a quantum spin liquid perhaps. And that was, our idea was that we could use pressure to induce a spin crossover. And so for quantum spin liquids, you want things to be as quantum as possible. And so a spin 5 halves is less quantum than a single unpaired electron. And so you really want to have a system that has just one unpaired electron. And we might be able to get to that if we could induce a spin crossover. And so you can induce spin crossover with temperature sometimes, you can't in jarosite, but we might be able to do it with pressure. And the idea is that we can increase the crystal field splitting so that the electrons would prefer to pair up than to occupy the higher energy orbitals. This is something that there are many papers in the mineral physics community. There are many minerals, iron-bearing minerals, that undergo this pressure-induced spin crossover. It's exactly the same phenomenon. We're just trying to use it to transform potentially our spin 5 half iron sites into spin 1 half. That's where that's the idea that led us originally to jarosite. And so what we find, so this is a plot of the unit cell volume as a function of pressure. And so if we look all the way up to 80 GPa, we notice 2 things, which are phase transitions. So if we have these dotted lines represent equations of state, and we find that in these 2 regions, we depart from one equation of state onto another. In other words, that equation of state cannot fit before and after these regions. And so we switch between equations of state. And so we know that we've undergone a phase transition. One of them is kind of hard to see, the other one's pretty obvious. So we have these 2 phase transitions. And so we wanted to investigate then what was the cause of these, and always in the back of our mind, we're hoping it's a spin crossover, because then that might mean we have spin half ions on a Kagame lattice. So the transition at 20 to 30 GPa, which we're showing in this animated GIF picture, we see a color change. This is piezochroism. As we compress the crystal, we see it change from this yellow to red. And so at first we were hopeful, maybe this is a spin crossover. It wasn't. And so the technique that we did many techniques, but the one that really shows this is X-ray emission spectroscopy. And so what we see is that over the course of compressing up to 75 GPa, so there are many spectra that I'm not showing here, I'm just showing the 2 extremes because it illustrates the point. But we did collect many spectra at sector 16, HVCAT with Yuming Zhao and Paul Chow. What we see is basically no change. And that's a sign that we don't have a spin crossover, because we would expect this K beta prime peak to disappear if we did have a change in the spin configuration. So that kind of rules out this being a spin crossover. In fact, both transitions are not spin crossover. And what we found was with UV vis spectroscopy that we have what we assign as a charge transfer band is moving into the visible region, which is what's causing this color change. So not as exciting as a spin crossover, but by using techniques, we're able to actually figure out what's going on. So what about the second transition? And so to figure this out, we ended up having to use infrared spectroscopy. So this was work done with Zhenzhen Liu at NSLS2. And so we performed infrared spectroscopy over the pressure range up to around 60 GPa. And what we see there is these, our hypothesis that we have these 4 regions where initially we have these 2 hydrogen modes, oxygen OH modes, that decrease in frequency and then start to stiffen at these pressures, becoming almost linear in this region. And then right at the same pressure that we see in the X-ray diffraction, this second phase transition, we see an abrupt discontinuity in the infrared. And so our hypothesis is that at this point, we are moving the apical oxygen from the sulfate group, so it's this oxygen in this rotating picture, we're moving it past the hydrogen in the OH group in the layer above. And that would then generate, we expect, 2 hydrogen modes where we used to only have 1, and that is consistent with now having 4 modes in the OH region where we used to have 2. So we think that this explains the data. And so that's, again, not a spin crossover, but it might offer new hope that a spin crossover is coming. This was the story of this project for 3 years. Maybe just if we go a little bit higher in pressure, we'll see something. This is single crystal diffraction data that show the environment around the ion. This is at 0 GPa, and as we compress, we were able to follow the single crystal diffraction up to around 30 GPa. We were able to follow the environment, this local environment of the ion, and what we see is that we are compressing preferentially along the equatorial oxygen. So these 4 oxygens, those bond lengths reduce much more than the axial bond length, which goes from 2.06 to 2.03. If this is too small, we're going from 1.99 down to 1.85. So significantly more compression in the axial direction. But what really we want to do is compress all of those at the same time to increase the crystal field splitting. This is the last slide. And so from the Mossbauer, so I told Erjan at the beginning that we would have some data. There's so much more data behind the scenes. I'm really condensing it into one picture. But this is showing the quadrupole splitting that we get from Mossbauer spectroscopy as a function of pressure. And the quadrupole splitting is a measure of the asymmetry of the electronic field gradient, which is due to the asymmetry of the environment. And so what we see is an increase with the initial compression, and then a discontinuity, and then a decrease. And so this is consistent with what we've seen from the single crystal data, that up to 30 GPa, we're just compressing the equatorial bonds and not the tetragonal. So it's a tetragonal elongation because we're not compressing those axial bonds. And so we're increasing the asymmetry and therefore increasing the quadrupole splitting. After the second phase transition, we now seem to be decreasing the quadrupole splitting and actually getting to lower values than where we started. So the suggestion might be that above 120 GPa, we're actually compressing all those bonds at the same time. And so we might actually see a spin crossover if we just keep going. But of course, we've both moved on from this project, and we'll see if anybody else picks that up and sees if that's true. Okay, and so with that, I'll stop talking. There are many people to acknowledge for the work that I've shown in this presentation. I'll mention a few of them. So of course, Dana, the group leader at Northwestern, was of course integral to the whole project. Steve Jacobson really taught us how to do high pressure. So I came to the high pressure community knowing nothing about high pressure and learned everything really from Steve. And the connections through CDAC, with him being a CDAC partner, are really what got us off the ground and able to actually do some of this really exciting science. And so I showed papers that were written and published by many other people in the group that are listed here if you want to know what they look like. There are many people at Argonne, there are many people that are probably not listed, and NSLS too as well, who have helped throughout these whole projects to get really, really exciting data with new techniques that we hadn't used before. So with that, I'll thank you for your attention and invite any questions.
Thank you, James, for a beautiful talk. Excellent. Nice that you highlighted so many themes that have emerged from these CDAC talks, from quantum materials to structure search methods, to electronegativity effects and so on, as well as all the different techniques that are now available. So I'm sure there will be questions. We had up to 80 participants. So feel free to unmute yourself and ask a question or use the chat box.
Hi, this is Shuai from University of Rochester. May I ask a quick question? Maybe it's the, oh, can you hear me okay?
Yes.
Yeah, I can hear you.
Yeah, thank you very much. So it's a more technical question. So MgO is transparent, right? So what mechanism that makes it cuttable by the laser? Maybe I missed that part.
I didn't go into that.
Okay.
So it's, I believe, an IR laser, and I don't know if Ross is on the line. You can correct me if I'm wrong. Yeah, I don't know the details of how it couples to be able to machine the MgO, because you're right, it's obviously transparent, so I would presume it's just not an optical laser, but I don't know the answer.
Okay.
But there's an excellent paper published by Ross Rubiak on that instrument. So
Okay.
I should get the details from that.
Thank you.
Yeah.
My name is Leonid Dubrovinsky. I do not know if you can hear me.
I can hear you.
Yeah. So thank you very much. It's very interesting talk. I have a couple of questions. You mentioned about modulated copper bismuth compound.
Yeah.
You found its ambient conditions. Is it still, or is it modulated at high pressure?
So those measurements were performed at ambient after recovering the sample. To be able to get that quality of data, we didn't put it back into the DAC to see if that changed with pressure. That's an experiment we could do. We didn't do that. So that's one data set collected at ambient pressure.
Okay.
That showed it to be modulated. Yeah.
Because you mentioned that it's not possible to see in the diamond angle, so that's probably not completely true. It's possible.
Possible. Yeah, the satellite peaks would probably be below the noise.
I mean, you should do single crystal, and for example, Maxim Bykov did it back in 2013 and over the years in single crystal diffraction. You perfectly can at least see and sometimes even solve and refine the incommensurate and modulated structures.
Yeah,
okay, there is one more thing which I would like to understand a little bit better. You use the only MgO as you called it, pressure transmitting medium.
Right.
First, I propose to not use term pressure transmitting medium because MgO is too hard. It's stress transmitting medium. But also, do you see any how to say effect of the non-hydrostaticity on the outcome of your synthesis?
We don't see an effect on the outcome. Of course, it's true that it's not a hydrostatic pressure transmitting medium. When we do laser heating, we tend to see that it anneals and gets us closer to being not quite so stress transmitting, as you rightly said. We haven't done any experiments to see if you did the synthesis with a different thermally insulating pressure transmitting medium, do you get the same materials? So it's possible then that I think what you're hinting at is that the stress gradient might actually be an influence on the chemical reaction. That's entirely possible. We have not tested for that. We tend to just assume that it's it's not an effect.
Okay, thank you very much. And just a small short comment in this respect. MgO at sufficiently high temperatures above, let's say, 2000, 2200 degree starts to change the oxygen fugacity in the cell. So it could be also interesting phenomena related to this. Thank you very much.
Yeah, thank you.
Thanks. More questions?
Yeah, I had my hand up. This is Ron Cohen. So very nice talk, really enjoyable. So just a question about your structure solving. You said one of your methods is database matching. Exactly what do you mean? Is that an automated process, or you mean just looking things up, or what?
The second one. So we just go to ICSD. You can search by reduced cell, or even just the cell that you index, and you pour through. You hopefully only get a few hits, and then you look at those and you see if there are commonalities between the structures that have a similar unit cell parameters within some threshold and what you found. And so with common structure types like the copper aluminium structure type, it kind of jumps out at you that this is a really good fit. And of course, we then do a revelt refinement with the atoms in place to make sure that the intensities make sense. So it doesn't end with the ICSD lookup, but in simple cases that can be an efficient way to get to the answer. In other cases, we have to move to more complex ways of doing that. But no, it's not an automated process. It's logging into the ICSD and searching chemical cells.
You just use X-ray data, or you use like Raman also, or anything else?
We collect Raman. We haven't used that to distinguish structures. That could be something that you might have to use other techniques to distinguish between symmetries. We usually just use the X-ray diffraction. With relatively simple structures, that's usually enough.
Okay.
In the case of the jarosite, there was certainly we had to read into the infrared to try and to be sure that we were still in the R3 M space group. And there's reasons from computational work done by Danilo in that paper that suggests that it's R3M. And so sometimes you can't rely on the X-ray diffraction data. You have to use other techniques.
Okay, thanks.
Yeah.
More questions? It was pointed out by Michael Dimkowitz that silicon is denser in liquid form, like bismuth. Another one is plutonium.
Okay, I'll take it back. Thank you.
More questions? Okay, well, if not, thank you very much, James, for a terrific talk.
Thank you.
Thank you all for joining us. We'll see you at the next one.